So most of us have probably noticed that pop-ups have returned to the web. On nearly every website, the moment you land, you are presented with a pop-up asking you to accept to be tracked. Today I'm going to talk about how we can dismantle this status quo and move beyond pop-ups. My name is Ben Brook, and I'm the co-founder and CEO at Transcend. So first we're going to talk about how we got here, and then we'll talk about how we can engineer our way out of this. So let's start with what went wrong. So web teams today rely on conversion funnels, and these are what track a user's journey from landing on the website to converting. And converting is like signing up or checking out of your shopping cart. But GDPR requires that websites get consent before collecting data about a user. So in order to actually get that full conversion story while complying with modern privacy laws, companies have to ask for consent as early as possible. And this is what has resulted in this status quo UX, where we are presented with a pop-up right away asking for consent so that the website can begin tracking and uploading data immediately and get that full story. And frankly, the pop-up remains the best way to get consent as early as possible. It's right in front of you, and you basically have to dismiss it to use the website. And the reason for this is because we need to start tracking as early as possible to get that full conversion story. And so does that mean that pop-ups are really the new user experience now and forever? We hope not. So to get past pop-ups, we have to be able to actually ask for consent later in the user journey. And so here's an example of a very simple and more natural user experience where it's using a standard checkbox in an existing form element to actually say, let's share. Can you share this information about how you arrived here? And this is analogous to things like crash reports, where if you've ever had an app quit on you unexpectedly, it will ask you to actually report that data up to a developer. And so to do something similar, we also need to perform local tracking. And that means that when the user arrives on the website, trackers are allowed to begin collecting data but not uploading it. So all of it is stored locally on the user's device, and only if the user provides consent can it be uploaded. But switching to local tracking is extremely hard because most analytics happen through third-party scripts like Google Analytics. And so when they're imported, these scripts will immediately begin tracking and uploading data about the user. And it's very difficult to alter the functionality of these third-party scripts because it's imported code and you can't really change it. And so how can we actually block these trackers from uploading data? What if there were a firewall? So if browsers had a firewall, then governance rules could be set to regulate all network traffic on the user's device. Essential network traffic, such as image loads, could be allowed through, but network traffic that's related to tracking the user could be blocked, at least until the user provides consent. And so even the third-party analytics scripts could run as normal, but the data wouldn't leave the user's device. And a firewall then is essentially converting all tracking into local tracking. Furthermore, a firewall could actually quarantine traffic. So when a tracking event gets blocked, it could be placed into local storage on that user's device so that later that traffic can be replayed if the user does decide to give consent and share information about how they arrived at that conversion point. And furthermore, the firewall could be opened up to allow any further tracking through. And so thus we're setting out on a journey to actually build a firewall in the browser. And this would keep all tracking local. It would allow analytics scripts to run on the browser as normal, but we would intercept any transmissions and save them for replay if and when the user gave permission to. So we went through a few ideas, and initially we sandboxed every script in its own lockdown iframe with a copy of the current document. This lockdown sandbox iframe can't make any network requests. And so on the left-hand side, when we see that script import, we actually create an iframe, a sandbox iframe, and import that JS there. And so that the JS can actually run, but no network requests can be made. And we actually will be syncing between the parent document and the sandbox iframe. So let's say the script in that sandbox is appending an image to the document. Before allowing that mutation to be synced back up to the parent document, we would actually inspect it to see if it would violate the user's consent preferences. And that's by inspecting this mutation record, which is being dispatched back up to the parent document. So when that dispatch happens, we actually have the opportunity to ask this question: would this DOM mutation violate the user's consent preference? So in this case, the DOM mutation is actually importing an image, which is in fact a pixel tracker. And so in this case, this would violate the user's consent preference if they had opted out of tracking, or if they had not opted in yet. And so that would be quarantined. If it does not violate the user's consent preference, then great, let's proceed with performing that DOM mutation right on the parent document and calling that URL. So this solution was great because it benefited from a simple implementation, but it really didn't scale well enough to keep up with any sort of performance demands. So as the site included more and more scripts, we were syncing way too many events back and forth, and the memory usage and CPU requirements became untenable. Our initial attempt here could cause site functionality to break. It could be the layout or even the functionality if the DOM mutations were replayed in the wrong order. And this meant that we could not support script async or script defer in a high performance manner without continuously synchronizing each sandboxed iframe document. So we needed to find another way to allow scripts to run while intercepting all possible data emissions. So our second idea was to generate dynamic content security policies, or CSPs. CSPs are a browser-level feature that provides total control over network requests. So using a CSP, the website owner can specify an allow list of URLs that the user agent is allowed to connect to. And CSPs are typically defined directly by the web server through an HTTP response header, but they can actually also be set through meta tags. And these meta tags can be generated at runtime. And so here we can see that we've dynamically generated a CSP meta tag by analyzing a list of domains that we believe this website will make requests to. And based on the user's consent preferences, we can actually specify the allow list. And so in this case, we can see that we're allowing network requests to any path on this URL, as well as another external domain, allowed-url.com. And so to provide some examples of what the CSP would look like when the user is opted out and opted in, when the user is opted out, we're only allowing essential URLs. So these are like image loads to get the logo for the website and anything like that. We may also decide to allow for a widget like intercom to be loaded for support purposes. But when the user is opted in, we actually expand that allow list so that we're also allowing the tracking URLs, so the user can now connect to LinkedIn ads or Google Analytics in this case. And so the CSP method was really great at blocking tracking attempts, but it does not offer an easy way to replay them once that user has provided consent. CSPs cannot capture HTTP post body data from blocked requests, which means that we can't reliably replay requests made from form submissions or JavaScript networking APIs. And furthermore, on a given page load, a CSP can actually only become more strict about where data can flow. So when consent is given, we cannot update the CSP to allow data to flow to new destinations like Google Analytics or something. And so we couldn't do that, at least not without a full page reload. The CSP method also raised an important question for us, which was, what should the default behavior be for unknown network requests? So should we allow that network request through and guarantee that we're not breaking something on their website? Or should we block it and guarantee we're not accidentally letting an analytics event through? CSPs actually will enforce the latter case. And while we believe this is an extremely rare corner case, we think that the default behavior should be up to the company. And so while the CSP method was excellent at blocking data emission, we needed something that could reliably replay events and handle consent changes seamlessly. And that brought us to our third idea, where we are essentially detecting JavaScript network API events by patching and overriding all of the global interfaces used to create network requests. So these APIs will include XHR, Fetch, Navigator.SendBeacon, and many more. And these patchers will actually evaluate the requests they're making and determine whether they should be blocked or allowed. We also need to detect any pending DOM mutations that may cause a network request. So here we'll have to patch the prototypes, methods, and accessors to all global constructors and DOM tree construction utilities. So to put that in layman's terms, that is like an image tag with an SRC attribute. We have to be able to actually patch the way that DOM mutation is performed when it gets inserted into the document. We need to be able to inspect that URL and decide whether or not that image is allowed to be imported. So let's dive into an example of this. So on the image.src example, we can write a patcher which essentially overrides the constructor prototype of the image constructor. So by doing that, we're actually able to check before the setter is run, or before the DOM mutation is performed. We can check whether this URL is allowed to be connected to. And if it is, great, we're going to import that image. If not, we're going to quarantine it. So if it's a pixel tracker, like on the right-hand side, that would actually be regulated by this patcher. And while that particular code snippet is regulated by a patch to the constructor, the second code snippet actually slips by. So in the second code snippet, we're actually inserting inner HTML into a div. And so this is a string of HTML, which again has an image with an SRC attribute. But interestingly, inner HTML does not use the image constructor. And this is actually true for all DOM APIs that take HTML strings as input, such as outer HTML and many more. And so for this class of problems, we had to think of something else. And so we actually patch these methods to insert nodes into a sandboxed environment first, using what we call virtual documents. And these are much faster than iframes, but they're also unable to make network requests. So when that setter for inner HTML is called, on the left-hand side, we can see that it's inserting two images. One is a pixel tracker and one is just the company logo. And that setter is overridden to actually create a virtual document where those images can be appended. But again, they can't make those network requests. We then check for any request-causing DOM nodes. So in this case, these are the SRC tags. And we again ask that same question: would this mutation violate the user's consent preference? If yes, then we quarantine it. So for the pixel tracker, that got quarantined because we identified it as analytics. And in this case, the user is not opted into that. And for the logo, we actually did perform that DOM mutation. And so on the left-hand side, we can see that div with the two image tags. The pixel tracker is just a placeholder, so there's no URL to connect to. And the logo is imported as expected. And there's a lot of stuff like this to cover. So there are a lot of JavaScript networking APIs like fetch, XHR, event source, navigator.sendBeacon, WebSockets, etc. There are many types of HTML elements that can cause requests. There are a lot of different parts of the browser stack that actually perform network requests. But for each of them, between patchers, virtual documents, and sometimes a little bit of CSP, we can cover everything. And this method was a clear winner. First of all, it's blazing fast. No CPU strain was there. There was no memory bloat like we had seen with those sandbox iframes. And we tested this method on the heaviest interactive websites, from popular webmail clients to video streaming providers and multi-user document collaboration apps. And there was no noticeable overhead. Furthermore, this is a complete solution. It actually is able to govern every type of network request. And replay works. So we can actually take those events that we've blocked and replay them later if and when the user decides to share the full story with the site owner. And all of this is now bundled into a software which we call airgap.js. And airgap is a firewall for the browser, which allows for policy-based data flow governance. And you can set rules based on consent, based on the type of URL, and really anything arbitrary. It's as simple as a drop-in script, and it's a 33 kilobyte payload. So we're really excited about this technology. We don't think privacy laws have to create really rough user experiences with pop-ups. We would love to see pop-ups go away, and we think technologies like this are how we can actually start dismantling such a status quo. So thank you very much. If you have any questions, please feel free to email me at ben.brook@transcend.io, or if you're interested in test piloting AirGap, please do reach out. You can also find me on Twitter at bencmbrook, or our company at transcend_io, and you can also visit our website at transcend.io. So thanks again, and goodbye.